Good evening, everybody. My name is Neil Pandia, and I would like to welcome you to the inaugural Cyberspectrum meetup, the Bay Area's new forum for software-defined radio enthusiasts. The event tonight is being sponsored by Edis Research, and your host tonight is Balint Sieber. There's free beer and pizza in the lobby, so please help yourself anytime. Tonight we have a great set of speakers. First, Julian Arnold, who is the Edis Research Intern of the Month, will do a show and tell and give a demonstration titled Broadcast Stereo FM Receiver Transmitter using GNU Radio. Your applause will be used as a gauge to determine whether or not he should be awarded Intern of the Month again for November. So please watch closely. Next, Kevin Reid will give a talk titled A Visual Introduction to DSP for SDR. Then Erik Olson from SigBlips will give a talk about Baudline, a time frequency browser designed for spectrum analysis and data visualization. And last, but not least, Balint himself will give a presentation about some spectrum monitoring code that he's been working on lately. Future meetup locations will alternate every month between here in South Bay and San Francisco. Next month, the meetup will be held on Wednesday, December 17 at Noisebridge, which is a hackerspace in the Mission District. Please check the meetup website for more details as the date gets closer. If you have any ideas for talks or presentations or demos, please let us know. And with that, I will pass things over back to Balint.
Thank you very much, Neil.
Thank you, Balint.
So thank you all very much for coming to the inaugural Software-Defined Radio Cyberspectrum meetup. Oh, thanks. I'm getting visual directions from Neil. Hope you're all enjoying yourselves so far. As Neil said, we have an exciting lineup for tonight, our very first. And I'm very excited. I hope you are. And I would really encourage you to sort of spread the word as you can. I don't know how many of you are sort of into social media and Twitter and so on. But if you want to take some photos and tweet during the proceedings this evening or later in the week, that would be wonderful so that we can get a bit of momentum going in the Bay Area. We're going to try and take it up to San Francisco next month on the 17th. To a famous hackerspace there and have people attend, and then we'll alternate back and forth because obviously it's not entirely convenient for people to be going back and forth the whole time. But hope you enjoy the show tonight. I think it'll be good, and if you have any questions now or later, please feel free to ask. And so first up, then we have Julian Arnold, Edis Research Intern of the Month, hoping to score that next as well. Self-proclaimed, by the way, I might add, self-proclaimed Intern of the Month. And for the show and tell slot today, then he's gonna show us some cool stuff. I'll hand it over and give you the. Let me know. Okay. Take it away, Julian.
Okay. Yeah. So, welcome everybody. Thanks. So my name is Julian. I'm interning with Edis Research, and as being an intern, I was not forced to do this. So what I'm going to talk about is how you can easily build your own FM radio transmitter using GNU Radio. And so what we are going to do, or what I'm going to do, is try to synthesize this kind of spectrum. So this is the FM radio spectrum, where you have here your mono audio channel, which is left and right channel added together. Then you have a 19 kilohertz pilot tone. And then you get your stereo signal, which is different signal. And here you've got the RDS, which I'm not going to cover, but which you can also easily cover with GNU Radio. So let me switch to GNU Radio Companion. So who does not know GNU Radio Companion?
Don't be shy.
Julian
will give you an extra quick summary.
Okay, so I would say most of the people know it, but some people don't know it, so I quickly explain. So GNU Radio is the graphical, or GNU Radio Companion is the graphical front-end to GNU Radio, which is a very convenient way to program your software-defined radio, which by giving you a lot of pre-programmed blocks that you can easily connect, and the framework will do all the magic for you. So this, what you see here, is everything you need for your stereo FM broadcast transmitter, excuse me. So And if you recall the spectrum that I showed you earlier, I will now explain to you how this is built up using GNU Radio Companion or GNU Radio. So we start here where our audio signal is coming in. It's just taken by this block from your internal audio device, so like your microphone, or like I'm doing it streaming from your speaker to your microphone and then into this block. Then it gets this just a multiplier, so the amplitude gets adjusted. You resample the signal to 380 kilohertz sample rate, because this is most convenient for all the other processing steps. And then here's where the first real thing happens. So we build the sum signal, which is the plain, which is used for the mono audio channel. And here we build with the subtract block, we build our stereo channel, which you've seen in the spectrum right on the right side of the 19 kilohertz tone. So then these get fed into low-pass filters because the resampler is not that perfect. So we have to sample here again. This, again, just a simple block, and you just like the cutoff frequency, your sample rate, and transition width, and you can specify the window to use. So pretty easy, pretty straightforward. So then we take our sum signal and just feed it in this adder block, because recall that this sum signal was sitting right at DC. So we don't need to shift it. Our difference signal, we multiply it by this 38 kilohertz sine wave, so it gets shifted to the right of our synchronization tone, which is here at 19 kilohertz. Gets multiplied by constant, and then these three signals get all add up here in this adder block, and this is for RDS, so we don't consider this now. Then you can easily hook up a graphical sync so that will display the spectrum, the baseband spectrum. And then we take our baseband signal, feed it in a frequency modulator, so which is doing the frequency modulation for us, and resample it again to adjust the sample rate to our, in this case, USERP, or whatever kind of software-defined radio you have, and then it's going over the air. And so in case you don't believe me, I will just demonstrate that.
We don't believe it, Julian. Hard proof.
So here's our USERP, software-defined radio. And I'm going to start the flow graph. So here you see our signal coming out. Now I apply some audio from my Spotify account. I don't know which song it is, so we will see that shortly. But again, here you can see the mono signal, which is starting at DC. Then our pilot tone, and this thing here is then our different signal, so the stereo part. Okay, so looks good. Let's try it out. Where's my receiver? There it is. Hopefully it's still working. As you can see, we're at 99.3 megahertz, so I just this here. And here we are transmitting. So, for example, you can adjust in real time every parameter you want to adjust. So, for example, the gain. Let's go down the gain. See? So it's a very, very convenient way of programming a software-defined radio and to play with it and just do things at runtime and visualize things at runtime. So this is what I basically wanted to show you today. So that's it. Thank you very much.
I have a question, Julian.
Yes.
How long did it take you to put that together?
Oh, not long. I would say like 2 minutes. Because to be honest, this code is available online. So I downloaded it, took a look at it, and used it. So if you want to download it as well, it's called GRRDS, and you will find it on GitHub. Question? Yes?
Yeah, what was the signal sitting just below 60 kilohertz when you were running the F15?
Which block you mean?
When you had the display before, when it was operating?
Oh, should I turn it on again?
Yeah,
On the
you
spectrum.
can see the left minus right signal, and then there was some larger.
That was RDS.
RDS.
So that was the RDS. So the digital information, which will in your radio in your car will like display the track name or the radio station name.
Oh, okay.
More questions? Yes.
This is not a question, but a comment, sorry. You mentioned that you do a resampler and a low-pass filter, and that shouldn't be necessary.
No, it shouldn't, but
however, there's a bug in the rational resampler where it doesn't compute the taps correctly, but if you just plug in your low-pass filter into the taps of the rational resampler, it should work just fine.
Oh, great. Thanks for the comment. So we were just, a few minutes ago, we were discussing, why do we need that low-pass filter? So the rational resampler should do the job. But
yeah, there's a bug where if you tell it to interpolate, it doesn't calculate a narrow enough filter. So
okay.
It's garbage.
Yeah, thank you for the comment. Good. Questions, comments? Oh, okay, thanks.
I might ask a little question. Can I have a show of hands just so we sort of get an idea? How many of you have actually heard about GNU Radio? Wow, that's pretty much, okay. Can I invert the question then? How many of you haven't heard about GNU Radio? All right, that's all right. No, don't be shy. Don't be shy. Everyone's welcome. And how many of you actually used it then? Out of who's heard about it? Okay, and sort of on a regular basis as part of their work. Yeah, all right, excellent. Round of applause. Your round of applause then will now be measured. So we can determine this. So it's all up to you now. Take it away. And if you're joining in online, please feel free to leave comments on the meetup page, and we'll use that to assess your performance. I think that was pretty positive. I think you might be looking at another month.
Month's great.
That's a
Of course,
good.
inside of the month gets to present next month.
Thank you, Julian.
No, all right, so I guess we'll now proceed on to our next speaker. Kevin, do you want to take it away?
Thank you.
I get the impression Kevin's been working on some mighty cool animated graphics to explain some.
I've been wanting to do this chair for a while, and this gave me a great excuse.
Hi. So one thing, I was thinking about this, and one of the things that you sometimes do when they're giving talks is, somebody comes up and introduces the speaker and tells about how they're a personal friend and what their credentials are. Well, I have no credentials. The only reason I'm here is because Fallon asked for presentation topics, and I came over and says, I'd like to do this talk. So the title of my talk, well, it's right there, A Visual Introduction to DSP for SDR. And as you can see, this is going to be a visual introduction because there's a waveform. Going to be playing with the audio. This presentation is intended to give a tour of DSP topics relevant to implementation of software-defined radios. This is not a complete introduction. If you want to do these things yourself, you'll probably want a book or somebody else's tutorial. The topics I've selected are those which are either particularly fundamental or which I felt would benefit from the style of animated graphics I'm using here. This is a depiction of amplitude modulation as usually understood. You've probably seen this sort of picture before. The modulating audio signal in black is offset above 0 and then used to control the amplitude of the carrier signal. That is, they are multiplied together, and the result is this signal shown in blue. Let's freeze it for a moment, and you can see, classic picture. Sometimes this wave is, in this context, is called the envelope of the signal. The problem with this picture, for our purposes, is that the math is messy. For example, if you were trying to demodulate this, every time the signal crosses 0, you have no data because the audio is multiplied by 0. Of course, in reality, the carrier frequency is immensely higher than the audio frequency, so it's easy to average over that. It's not that it's infeasible to work this way. You can, in exact analogy to analog RF electronics, but there's something else that you can do that's much more elegant all around.
It doesn't matter as much for AM. Sorry, I seem to have written the wrong text in the wrong slide. But anyway, so, well, actually, that's still true, yes. So the difference doesn't matter as much if you're just doing analog AM or FM, but I'm using these because they make good pictures, not because it's the best example. So here we have a signal which has values which are complex numbers rather than real numbers. The carrier wave is complex sinusoid. The real part is a sine and the imaginary part is a cosine, together making a helix. On this plot, the real and imaginary parts are labeled I and Q. These are the conventional names in signal processing. They stand for in phase and quadrature. This can also be called an analytic signal, which means roughly that it has this helical structure as opposed to, say, being a real signal that we usually see simply rotated into the complex plane. The modulation works exactly the same way as you already seen. Multiplying the complex carrier by the real audio varies the magnitude of the signal. We will see later how this picture corresponds to physical radio signals, which of course are not complex numbers, or they are depending on how weirdly you want to look at it. So let's have a little more look at this. This is what frequency modulation looks like in the same setting. The blue curve looks like the conventional picture of frequency modulation. You can see the cycles coming closer together and farther apart. Testing. Come on. There we go. You can see the farther apart here, narrow together here. The black line is again the signal before we add the carrier wave, but this time you can see it's moving around the circle. It's varying the frequency. It's varying the speed of rotation in the complex plane. When it's moving the same direction as the frequency. The output frequency becomes higher. When it's moving the opposite direction, the frequency becomes lower. If we want to receive and demodulate this signal, we want to get rid of the high frequency carrier wave. In a real radio, rather than this picture built for readability, the carrier frequency is immensely higher than the bandwidth of the actual signal and would like to not deal with the processing requirements of that high frequency. And also to be able to tune anywhere on the radio spectrum and treat these signals the same way. We do this by multiplying the signal by another complex sinusoid, here shown in red, of equal and opposite frequency. This is a negative frequency. The helix is wound the other way. You can also call it the complex conjugative carrier, that is, the imaginary component is negated. This cancels out the original carrier wave. As you can see, we have the previous, what we're showing in the black is now the blue signal, which is the modulated signal having been transformed back. In general, this technique allows you to change the frequency of an arbitrary signal, adding or subtracting an offset. And the offset is whatever the frequency of the wave you multiplied it by is. When the signal is moved to be centered at 0 hertz, because remember, we have negative frequencies here. That's what complex signals get you, essentially. When it's at 0 hertz, it's known as a baseband signal. By the way, if you ever heard that base in the names of Ethernet speeds, it means the same thing. It's not modulated on a carrier. Anyway, up until now, the pictures I've been showing you have had solid lines. This is an accurate depiction of analog signals, but in DSP, we are working with only a finite amount of data. The signal is sampled at fixed time intervals, producing a sequence of numbers. This graph is the exact same signal, showing only the sample points. Generally, you want the sampling rate to be as slow as possible to minimize the computation needed. However, there's a fundamental limit known as the Nyquist frequency. And by the way, stop me if you have any questions. Or if it's just not making sense, feel free. Okay. Sure.
You were showing what the waveforms look like for the various different types of modulation.
Yeah?
And when you had a complex value FM, you didn't stop it and show us, allow me to visualize that stop.
Okay. Well, here it is. So if we look at the, unfortunately it doesn't work as well. Yeah, there. So.
Kevin, sorry, I'm going to ask you if you have a question. The mic will be able to pull it up if you could.
Okay. Yeah. The question just wanted some more details on the complex frequency modulation. So, okay. So here I've rotated it out. So this black line is not the original audio, but let's say it's the modulation before you add the carrier wave. So, but this is almost the original audio. But what's happening is this is actually rotating in the complex plane. Let me turn it around so you can see it. If you look at it end on, you can see how it's going around the circle. So what's happening is if you have two complex numbers of unit magnitude, then basically the angles add. So when you multiply them together, the angles are added, and that's what's happening here. So if the carrier wave is going this way, and the audio is going this way as well, then the frequency increases because together they go around faster, and vice versa. Does that help? Okay. Let's see. So as I was saying, for digital signal processing, you have to sample the signals, and there's a fundamental limit on how slowly you can sample a signal, known as the Nyquist frequency. What you're seeing here is the instantaneous value of a sampled signal, one sample, except we're showing it in time rather than along in space. The signal is a sinusoid with a frequency which is continuously increasing. As it increases, it appears to reverse because the frequency is so high that it completes more than half of a complete cycle between every two samples. This is the Nyquist frequency, 1/2 of the sampling rate. A signal of some frequency f, when sampled, is exactly the same as a signal of frequency f plus the sampling rate. Frequencies in digital signal processing are points on a circle. They are modulo the sampling frequency. We usually think of them as having a range from minus the Nyquist frequency to plus the Nyquist frequency because that symmetry is useful. But since nothing in the math and physics respects that limit, we have to do it ourselves by filtering. In a software-defined receiver, we filter using analog circuits to remove frequencies above the Nyquist frequency before sampling the signal, because if you try to remove them afterward, you can't tell the difference. This removes the ambiguity and allows us to treat the frequencies in our digital signal as if they were not circular. Filtering, as I just mentioned in the analog domain, is also useful for digital signals to allow us to reduce or increase the sample rate. Again, as I said, you want to keep the sample rate as low as possible, but sometimes you're doing something that requires you to increase it, such as, for example, when you add the carrier wave to the audio, you need the high sample rate to cover both of them. Or filters can separate a particular signal from nearby irrelevant signals and noise. Digital filters can be much more precise than analog filters, and they can be adjusted by changing data rather than changing circuits. To illustrate filtering, here is an example signal, which is the combination, the sum, of two components of different frequencies. It looks very far from a nice helix, but you can still easily see the two components. Practically, good digital filters can extract signals that you just can't see at all in a plot like this. A simple and widely useful class of digital filters is finite impulse response filters. FIR filters operate by taking delayed copies of the input signal, scaling them, and adding them together, a sort of carefully designed moving average. That's all there is to it. In this picture, the copies have amplitudes of 1/3, 2/3, and 1/3. You can see, so here's a low P, 1/3, 2/3, 1/3. Then if we add these three signals together, the result contains mostly the low frequency component of the input signal and not the high frequency component. This kind of filter is called a low pass filter. It's not a very good one. Good filters have systematically chosen coefficients rather than just 2/3 and 1/3. I just threw those numbers in, and they have many more coefficients. These coefficients are also called taps, and they're also called the impulse response of the filter. And the count of them is called the filter's order. If instead of adding the three copies, we subtract the outer ones from the middle one, the filter becomes a high-pass filter, keeping the high-frequency component instead of the low-frequency one. So you can see this high frequency is becoming very close to the Nyquist frequency for this sampling rate. You see because the peaks are irregular. That's because this peak fell on a sample and this peak fell between two samples. So this is actually a perfectly good signal. It only looks like garbage because this connecting sample dots by straight lines is not the proper way to display a signal. It's just easy. There's better information in there than it looks like. A so-called infinite impulse response filter, as opposed to works exactly the same way as a finite impulse response filter, except that in addition to summing input samples, it has feedback from its own previous outputs. IIR filters can be more efficient than FIR filters by having a lower order, fewer taps, that's requiring less computation, but they have additional hazards such as instability, runaway feedback. As a side note, you may well have used an IIR filter yourself. If you've ever implemented an average like input times 0.1 plus previous output times 0.9, that's an IIR filter of order 1. Here's some filters applied to the live audio. High pass in green, low pass in red, and the original audio in blue. So let's say something, and you can see that the red curve is following the general trend of the blue curve, but not the little bumps. And the green is showing the little bumps, but not the overall curve. And that's a filter. So on a topic that I don't have a good segue for, the discrete Fourier transform, commonly referred to as the fast Fourier transform, even though that's actually the name of the algorithm for implementing it, converts a signal in the form of an array of samples over time, which is what we've been working with so far, into an array of samples over frequency at not exactly one moment in time. This enables visualization and analysis of unknown signals, can be used to implement filters, and you could argue that the FFT is the foundation of modern digital signal processing. You could. You can do lots without it too. First, let's have a large number of copies of the input signal. In reality, we would have a number equal to the length of the input array, but for this illustration, 21 will do.
I have a question.
Yes?
From the internet, actually, if you don't mind me interjecting.
Sure.
What software is he using to give this presentation?
Okay. The question was, what software am I using to give this presentation? And the answer is, I wrote it myself. The entire thing is a web page. The graphics are done using a visualization library called MathBox. And the DSP is all just handwritten in JavaScript. You could do that these days. It helps that we're doing audio frequencies and not radio frequencies, so it's actually, everything here you see is running at a maximum sample rate of 44.1 kilohertz, because that's the sample rate that my browser happens to present to it. But of course, a lot of these actually have been quite downsampled. You can see the lines if you look. So yeah. Once you know how the math works, it's not hard to do this stuff yourself. Though actually, I wouldn't want to implement the FFT from scratch. This is not FFT. This is the really inefficient way. Anyway, so as I said, we have 21 copies of the input signal. Then we multiply the signals by sinusoids with equally spaced frequencies. The copy remaining at the center has frequency 0, so it's unchanged. As we saw earlier, the effect of this is that a signal with equal and opposite frequency will be untwisted, becoming a signal with constant phase. It does not rotate around the axis. It's all on one side. Now, if we look at these signals end on, discarding the time information, we can see which ones are least twisted. These are the closest matches to the frequency components in the original signal. So let me demonstrate. I am not very good at whistling. But you can see that these things are mostly wobbling wildly, though making nice spirograph patterns. But these two right here, you can see that these are mostly on one side of the axis. These are the closest matches in this discrete Fourier transform to the pitch I was actually whistling. So you can see one of them's a little bit on one side and one's a little bit on the other side. So let's see. Unfortunately, it's not easy to just plug a signal generator on here because my microphone actually has noise canceling that takes it out if you feed a constant signal in. Yeah. Good. Do that some more. Yeah. Actually, one thing you can do is just play some music while this thing is turned on and just yeah. Anyway, so the next step. The final step is to sum these signals over time. When the frequency doesn't match, the samples cancel each other out, so the output values are close to 0. Where the frequency does match, here you can see these two, the samples combine and produce a large output value. At this point, we have a complete DFT. If we took the red lines above, oriented them in the same direction, discarding the phase information, and made the lengths logarithmic, we would then have a spectrogram, exactly as a spectrum analyzer or STR receiver application displays. The fast Fourier transform is an algorithm for implementing the DFT that we have just seen efficiently. The naive implementation I just described here is quadratic in the length of the input, which you don't want when you're doing real-time signal processing. This graphic also shows the relationship of complex valued signals to real signals. The spectrum of a real signal is always symmetric about 0. You'll notice this is always flat. That's because it's the real signal that was multiplied by a complex signal of frequency 0, so it never got rotated into the complex plane at all. A real signal is always symmetric about 0. A real signal cannot distinguish negative frequencies from positive frequencies. And that's why, if you're not doing GSP, you've probably never heard of negative frequencies. Now, a real sinusoid is equivalent to the sum of two complex sinusoids of opposite frequencies because the imaginary parts cancel out, leaving the real component. And unfortunately, that's all the pretty pictures I have for you for the moment. But I'm not quite done. Now you'll get to see some of my old presentation, which will have some discussion of how you actually use this stuff. So here is the software architecture of a software-defined radio. This is a block diagram. You have some hardware, or more precisely, since we're talking about the software, you have a hardware driver. So one thing we can do with it is we can take the samples from that hardware driver. We actually have to break them up into chunks. I forgot to include that step. When we take the chunks over short times and stuff them into an FFT, and then we put that on the screen. And that's the waterfall display or the pan adapter or whatever you want to call it that you've probably seen every time somebody mentions software-defined radio. It's the icon of it. So that lets you look at a bunch of stuff. But if you want to actually listen to a signal or decode the digital data or whatever, you do exactly this. Your first step is, as I said, complex multiplication. Because all of these black lines except for that one, represent signals. And this is a complex signal. It gets multiplied by a complex sinusoid generated by, classically this is called the local oscillator, but it's really just a thing that it's just computing sine and cosine a whole lot. And you multiply them together. Or there's actually more efficient ways to do that too. Then you put it through a low-pass filter. It's also a low-pass, and the low-pass filter, what it's doing is it's removing all of the signals that just came in from the hardware that are not right next to zero, because we want to. So this allows us we select the signal we are interested in by generating that same frequency as the carrier frequency of that signal, multiplying it together to bring that to zero, to baseband. Then we use the low-pass filter to remove everything else. This is a decimating low-pass filter, and that means it is reducing the sample rate. You can do that because the low-pass filter got rid of everything else, so we're not losing any information by using a lower sample rate. Then we use a demodulator. What exactly the demodulator does depends on whether it's AM or FM or OFDM or whatever. If it's AM, it's actually just exactly as simple as you take the magnitude squared of the complex samples. That's all you have to do. If it's FM, it's a little more complicated because you have to look at sort of, because the frequency will be not exactly zeros. You have to look at how fast it's going around. But the math is still quite straightforward. And then coming out of that, you have a real signal. You can pipe that out to the audio. You're done. And parts of this that you need to be able to control, well, there's lots of controls you can put in there, but the fundamental ones are, first of all, you got to specify what kind of demodulator you want. You got to specify what frequency you want to select for demodulation, and you got to tell the hardware what frequency you want to bring in so that you can look at. And this has to be sort of within that region, because otherwise you're not receiving it at all. In some cases, for example, an SDR designed for HF, for high frequency signals as the amateur radio operators use for worldwide communication, those are all below 30 megahertz by definition. And it turns out that 30 megahertz is a reasonable sample rate you can just pipe into your computer if it's a pretty beefy computer. And there are commercial SDRs that actually work that way. So in that case, you don't actually have this frequency control line. You just take everything all the time, and then in software, or maybe whether it's software on your computer or your desktop computer, or whether it's software built into the radio, handles all the processing. And that has the great advantage that you can look at everything all the time and say, oh, there's something. Click, I'm listening to it. If you don't have that much sample rate, you have to pan across the spectrum. Actually, I got a little ahead of myself. Let's talk about hardware architectures. This is the ideal hardware. You take an antenna, you stick it into an ADC, you shove samples in your computer. The price of this increases with the frequency you want to receive. Well, actually, that's true in general, but this is particularly bad. So instead, we have, again, these are now diagrams of the hardware, not the software. So again, we have a local oscillator which generates a frequency. We multiply it by the input, and we filter it for sampling. We sample it, and we shove it in the computer. So in this case, the driver is telling this thing what frequency to tune to. It's also maybe telling this thing how wide the filter should be, and this thing what the sample rate should be. Now, the catch with this is it doesn't actually get you a complex signal. It gets you a real signal because this is a voltage. Voltages don't have imaginary components, at least not that we care about. So you have to do something slightly more complicated. And this is how you get a complex signal from the physical world. What you do is you take the signal twice, you multiply it by two different signals. And these signals, well, if this one's a sine, then this one's a cosine. Or in other words, it has a 90-degree phase shift. And it works out that after that point, the effect is you get a complex signal. Then you filter and IDC it, and you get the two components that are called, as we mentioned previously, are conventionally called I and Q. And then we can do software processing exactly as we were as I mentioned before. Let's see. Yeah, okay. Well, I'm out of slides, so let's go to some more pretty pictures. Let's see. So this is just for fun. This is a live FFT of the audio in the room. This is a good one, not the stupid implementation I showed you before. And you know, looking at this thing can teach you some things about signals and harmonics and so on. And you know, but well, let's just not stare at the hypnotizing scrolling display for a while. So I'm out of material for the moment, so you can ask me questions, or if you want, I can show you my SDR receiver application. You can see how much signals we can receive with an antenna inside the building, or you know, if there's anything that you'd like to know about that I didn't cover or that I just skipped over, let me know.
I think, what about a round of applause for some
Hey, you're intern of the month.
I've got
Thanks, I already have a job.
I've got some comments for you from the internet, actually. On Pounding a New Radio, the way he lets us visualize this stuff is priceless for someone new to this like myself. I do really love the world SDR is opening for me. I love learning, and this is giving me reason to tackle math I never have, and RF itself is really fascinating. And he goes on in superlatives.
Thank you. And the one thing I'd like to mention, you know, like I said, all of the DSP in the presentation you just saw was written by me this Saturday in JavaScript. It's not hard. The most complicated thing I wrote was a routine to do complex multiplication. And you know, and the filters are just, you know, you add, you know. Now, it was a little simpler because it's not exactly a real-time signal system. What it does is it repeatedly captures a series of samples and just processes an array and forwards it on. But I basically built my teeny little version of New Radio in JavaScript. You know, it's not that hard. And of course, on the other hand, if your platform allows you the option to use New Radio, I do recommend it. It's a pretty nice tool for building SDR applications. And in fact, let's see. So,
Quick question.
yeah.
Did you write this in JavaScript too?
This, yes, actually. The audio here and the FFT processing is actually being done by browser APIs. There's something called the Web Audio API, which lets you do things like access the microphone, and then you can build a flow graph, actually much like you do in New Radio, except it's all intended for audio processing. The sample rate is fixed, but it has a component which will get you FFT data, and so I'm doing that here. 2,048 points. I actually throw away a bunch of them because some of them are too high frequency that they don't show you anything interesting. And now, the graphical displays here are actually ones I wrote for my SDR receiver application, which has a web interface, and these are both using WebGL. But you perfectly well do it with 2D Canvas APIs too. You know, so it's just you have an array of numbers representing the intensities, and you know, just draw a line, or in this case, draw a color.
Do you have a GitHub for this stuff?
Yes, you can go to github.com/kpreid, or you can follow links from my Twitter account. You know, I try to be reasonably visible on the internet. You know, and the presentation is not public. I have not yet cleaned it up. It is embarrassing right now because, like I said, I wrote it on Saturday. But my SDR application is public, and so we can happily use this thing. And you can see the source code for this, including the widget right now. Oh, let's see. It's slightly glitchy. Why is it? Okay. Actually, I think I want to blame the HackRF for this one. Let me just restart it. Okay, so here we have, of course, the classic demo, which is you have an FM radio receiver, and we can clickety and Why do I have no audio? Because the volume's turned down. And there we go. Yeah. So it works a lot better when you've got a decent antenna. But so as this application is built on the principles that I just discussed. This display is generated using an FFT. This mark here is the frequency. The hardware is local oscillator is set to. This mark here shows the offset that the software local oscillator is set to. So there's this part we can view. So we can view a large frequency and select one signal to decode. Let's see. Let's see. And let's just zoom out. And you can see this is using a HackRF unit which has a maximum sample rate of 20 megahertz, but for the moment I have it set to 4 megahertz. But you can see 4 megahertz gets you quite a bit of the FM band, and we can just so if we can go wherever we want to just go across the spectrum. There's more and. So, okay, let's see. Nope, just noise. One of the things you learn is analog hardware is not perfect. You will get garbage in some places. These are historically called birdies because they're little things that chirp from inside your receiver. Anyway, another question?
Yeah. Question back here.
Yeah?
Sorry, could we get the link to the GitHub again, please?
Could you put it on the page, on the meetup page?
Sure, that's a good idea.
You've got your Twitter there, your website, but not your GitHub.
No, but I mean, if you put it on the group page, we could all get it after.
Yeah, okay, I'll do, okay. Yeah, that's
You should complete your URL. That was a cool trick.
okay.
I think we can all agree that you are a hacksaw, that's for sure. Yeah.
So, any other questions? Yeah. Guess not.
That was unreal, Kevin. Thank you very much.
Yes.
I think you
Thank you.
And for a Saturday as well, right? It's just a Saturday?
I had the idea a while ago, and I had the previous presentation a while ago. The Saturday was the animation version. Anyway, but also, I will take suggestions if there's something else you like covered in this style, and I understand it, of course.
All right. Well, that was amazing. So let's take a couple of minute break then. I think there's still lots of food and drink outside. Just stretch our limbs. And then next up we have at Cyberspectrum, Erik Olson, creator of Boardline. He's going to show us some pretty cool stuff. So Erik, at your leisure, please.
Okay.
For our next presentation, we've got Erik Olson, the creator of Boardline, who's going to show us Boardline and some very interesting signals that he's analyzed with it in the past. Let me put the... Okay, take it away.
Okay, hello there. Tonight, I'm going to talk about these 5 topics, and let's get started. I run a company called Cyberspectrum DSP Engineering in Cupertino, basically contracting consulting, do some custom software development, and the main reason I'm here is I'm the maker of the Boardline Signal Analyzer, and I'm going to be using Boardline for all the slides you're going to see. It's a time frequency browser designed for scientific visualization of the spectral domain. You can read the rest. It runs on BSD, Linux, macOS, and Solaris. And well, here we go. First signal. SteadyQuest is a project that was started when Jill Tarter won the TED Prize several years ago, and she announced it to the world, and she called it, she wanted to empower Earthlings everywhere to become active participants in the ultimate search for cosmic company. And had a website. I joined it, and the real draw to me was they had ATA radio telescope data that they put on the web for people to download and analyze. And you know, I'm just a small software developer. Getting radio telescope data is a treat. And I had the opportunity to learn from the SETI Institute scientists, and I just couldn't pass that up. And I don't know if everybody knows what SETI is, Search for Extraterrestrial Intelligence. And I view it as the ultimate DSP challenge, because you don't know if it exists, you don't know what it looks like. There will be an extremely weak signal, and it's the classic blind search. So it has all these elements that make it incredibly challenging. First signal from SETIQuest, they called it Kepler XO4. The Kepler telescope is a satellite they sent into space to look at around the Cygnus constellation, and was just going to stare at this one spot. And it would took pictures of all the stars, and they wanted to look at the stars blinking. And the blinking meant that planets were going around. So Kepler XO4 was about one of the first stars that they detected planets around. And the SETI Institute pointed their Allen telescope array at this and collected some data. And it was one of the first data sets they put on the internet. Recorded at 1420 megahertz. In SETI lingo, this was called the water hole, because it's equidistant. Well, it's near hydrogen, and then oxygen is a little higher in frequency, and there's a lot of theories why extraterrestrials might communicate at that frequency. But in any case, what we're looking at here is baud line, frequency across the top, time down the bottom. The signal in the middle is hydrogen. And on the top, we have an average display of everything below it accumulated. So we can see the hump of hydrogen, and there's some RFI. So just browsing around this signal with baud line, I found this, which surprised people because they didn't expect this to be in the signal. And what it is, it's slightly drifting, and it's jumping between two frequencies, a high and a low frequency, and this is phase shift keying. So after saw that, I used a feature baud line has called the periodicity bars, and basically put up these bars here that are equally spaced, and you can see each of the high and low frequencies marked on the space line up perfectly with this, which means that we have completely stable clocking of these different symbols. And the baud rate was measured to be around half a baud, which is pretty slow. So then we demodulated the bits. Those are the bits we got. The SETI people got really excited because they didn't expect this to be in their data. We tried to figure out what these bits meant, put it on the internet, hoping somebody would see some framing or some sort of coding that looked familiar with it. We didn't come to any conclusions. They searched the Kepler star several times, and they didn't see it again. And if anybody recognizes anything in this bit, please let us know, because we still don't know what the signal was.
Erik, one quick question. You said it was phase shift keying, it was really XK, right? When you spoke, you said phase shift keying.
Yes, frequency shift keying, yes, not phase shift. So I want to go over the steps SETI goes through to determine if it's really a signal from outer space. First, you detect the signal, you measure its characteristics, and one of the first tests they do is the signal drifting? And the signal drifts if you're looking at it from outer space because the Earth is rotating and you get a Doppler drift, a Doppler shift to the frequency. So one of the first criteria when they detect a signal is it drifting? If it passes that test, the SETI people then do something called the on-off-on test. So you're looking at the signal, you see it, they point the
antenna away from the signal, and they expect it to go away. When they point it back at the signal, it comes back. They do that several times just to make sure they're not being tricked or there's a malfunction in their hardware or something. And if it passes that test, they want to see the signal a couple hours later. It has to be reproducible. And unfortunately, with this FSK signal, it didn't reproduce. If it did, they would have contacted other radio telescopes around the world. But we got all excited about this signal and never saw it again. And that's basically just as good as not seeing it in the first place when it comes to SETI. It needs to be repeatable. Okay, another signal we look at SETI Quest was the Voyager 1 signal. It's 130 AU from Earth, takes light 18 hours to get to it, and then 18 hours to come back. 8,400 megahertz. It's a really weak signal, and the SETI Institute looks at Voyager to test that their equipment is operating correctly. They want to make sure the antennas are pointed correctly, the beam forming is done properly, and all their detection equipment is working. So they look at Voyager once every couple weeks. Voyager signal is very weak. If you look at the green plot, that's just an accumulated Fourier transform of the spectrum. You don't see any signal. Broadline has a feature called auto drift that I wrote many, many years ago for looking at SETI at home data, which is not related to the SETI Institute. That's a Berkeley operation. But I didn't write it for them. I wrote it for looking at their data. But basically what it does is you have a signal that's drifting in frequency, and auto drift tries different solutions to the Doppler drift. And it found a peak in the signal. And then once it tells you where the peak is, we can look at it in the spectrogram, and the signal is drifting in frequency. Another SETI signal, another exoplanet that was detected around a star. They pointed their telescopes, looked at it. This signal has a lot of distortion and artifacts, something called a random drifting walk, and something strange. Here's hydrogen in the middle again, an accumulated spectrum at the top. Looks a little lumpy and has a little slant to it. That's just an artifact of the SETI Institute equipment at the ATA. So I zoomed in a section of it. You see a bunch of RFI. Looking at the RFI, you do some measurements, and you can see that which frequencies are related to which. Call these sidebands, but they're basically distortion products. And this is really useful when you're looking at the SETI Quest data, just picking out signal from distortion. Wandering a little over in the spectrum, we find a lot of random drifting walks in the signal. And the signal just kind of oscillates randomly left and right. We think these signals are caused by nearby electronics or oscillators from computers bleeding in. They're not signals from space. And unfortunately, they're a very common signal in the SETI data. And you have to come up with techniques and strategies of how to ignore them. In the signal set, browsing a little farther, we found something odd, and that's in cyan, because looking at these harmonics here, I colored those in cyan, and that's where the signal is. So zooming in a little bit more, we found this, and this it's just another odd looking signal. It has periodic symbol spacing, like the first FSK signal. But what's weird about this one is it has a variable symbol rate. So instead of a constant clocking, it jumps between two clocking rates that are not related. And just when I first saw this, it just seemed like a strange alien-looking modulated signal. But since something's strange, you're looking for SETI data, that really doesn't mean anything unless you can prove that it's coming from a particular point in the sky and it's reproducible. So even though this was interesting, didn't mean anything. Another great signal that we looked at with SETI Quest was the GOES-11 satellite. GOES-11 is a NASA weather satellite, and it is a great signal to look at because it has an incredible number of modulated signals in it, as you will see. Okay, here's the spectrogram of the signal. We have some signals here, here, signal there, here, a whole bunch of stuff here. And I'm going to jump around and start from the left and look at a couple of these signals in. This is an average spectrum of what we were just looking at. And the first place we're going to look at is this section right here in the middle, particularly these peaks, this hump, and this peak. Which turns out when you in on it, see how these are shifting? This is actually FSK with distortion products. So something went on when this was recorded at the ATA, probably parts of the signal were too strong and something was overloaded. So what we just looked at was FSK, and this is the average spectrum of FSK. You have the low frequency and the high frequency. And for some reason, this was wrapped around that hump in the middle, which is a binary phase shift key signal. What I did here, display, which basically takes the quadrature signal, you tune to your signal of interest, and when you're demodulating a signal, that's called carrier lock. Locks your carrier, and your two symbols, in this case, are clearly visible. Another part of the spectrum we looked at, strong tone-like signal here, a bunch of stuff going on here. I'm going to look at the signal on the left. And when I look at it with an IQ display, we get two distinct blobs like we had with binary phase shift keying, but there was a carrier in the middle that was not suppressed, and that offsets it. I call it offset BPSK because I didn't know any better, but it turns out NASA's been using a lot of signals like this, and the signal is probably 60-degree by phi PSK. So it really is BPSK, but it's constructed differently, so it has this offset. Another part of the spectrum we were just looking at has all these little signals in it. I'm going to jump around into some of those for a closer look. Each of those dots is a little signal we can zoom in on. Over the spectrum a little bit, we have this. And I'm going to zoom in a section of that. Bunch of little signals that appear in bursts, different durations. You know, things are divided nicely on different frequencies. So this is a sort of frequency division multiplexing, where you have your different modulated frequencies on different frequencies so they don't interfere with each other. Zooming into that a bit. Saw this, which is a strong carrier with a packetized data, and we have a LEO that just happened to fly by. LEO stands for a low Earth object, so it's a low Earth satellite that's broadcasting, and it just happened to fly by overhead. That causes the Doppler drift, and it was broadcasting, which was causing the tone we see. You know, just an accident that interfered with the data collection. Kind of a neat thing to see. And when I use the IQ display on the signal on the bottom, that this cuts right through, damaging part of the signal, we get BPSK again, and it's a little bit mangled because you had a strong tone running right through the signal. A little farther to the right in the spectrum, we have this. What's interesting about this is you have the packets of about equal duration. You have a strong tone here, which is your carrier. You look at this in the waveform display. It's kind of like a sine wave. But then you have these places where the phase changes abruptly. So it definitely looks, I mean, this definitely looks modulated. This definitely looks modulated. And when you put it in the IQ display, you see 8 distinct positions, and this is called 8 PSK. Okay, a little farther in the spectrum again, we run into this strange looking signal, which was really great to see because we saw this about a year before in a different signal. We still don't know what it is, and I will get to this in a later part of my talk. So what we did is we had just, all those signals that we just looked at were all in this. And this is just a fraction. What I showed you is just a tiny fraction of the different types of modulations and signals in the GOES signal. So you need a fairly big antenna to get a clean capture of this, but it's a great signal to look at if you're starting in DSP and you want to, kind of test your signal matching skills, signal detection skills. Okay, that's it for SETI-Quest. This summer, you've probably heard about the IC reboot project that Balint was part of. Did some amazing work on that was just incredible to watch. My interest in it was at the SETI Institute, they regularly look at the Voyager satellite as a test calibration tool of their equipment. The IC satellite and Voyager were both created and launched in the same year, around 1978. So they're the same vintage, and they have the same modulation types. So when I heard Reboot was coming around and they were going to talk to it, this was a great opportunity to look at a signal, modulated signal, the same vintage that Voyager was. So talked to Balint, and he said, here's some clean data from Arecibo. I'm all, this is awesome. I get to look at clean data from Arecibo. So now I know what a signal from Voyager would look at if we were really close to it, because the signals we get at the ATA are extremely weak. And my goal was to learn from this so we can better detect the Voyager signal at the ATA. Okay, so the first signal is just when they turned on the transponders on IC, it started sending back data, and we have a non-suppressed carrier with a modulation mirrored on both sides. Tune the IQ display to it. We have the same offset BPSK, or as NASA calls it, 60 degrees by 5 PSK. Another thing that's cool about this is you can see the spacing. And this is the frame spacing of the different packet structure that IC uses to send its telemetry data back. But it's really cool that it's very similar, and you can see the repetition rate. Okay, so zooming in on this, I got this. And you can actually see, there's Doppler drift because the Earth is rotating and IC's in space. We can measure what the Doppler drift is. And the oscillation is because IC is spinning. So if we go back to this picture of IC, this is I think the antenna that's sending data back home. And this is the axis of rotation. So it's spinning around like this with these 4 huge arms sticking out. And this is very different than Voyager, because Voyager doesn't spin. Voyager just has a big antenna, stands still. IC spins. And the spinning is what causes this oscillation, and you can measure it, again, with the periodicity bars. You get a nice accurate measurement of the spin rate. So that was really great, impressive. And what was cool about this is the telemetry that's in this signal that IC is sending back tells you all sorts of things about the health of the satellite. It has accelerometers, which is telling you how fast it's spinning, how much fuel there is, stuff like that. And the measurement I measured here matched what the telemetry was saying to, I forget exactly, maybe 2 decimal points of accuracy, which is really great because, that I could measure something like that. I was surprised. And it also verifies that the accelerometer data that is coming back matches. So it's another thumbs up that, this looks good. The numbers we're getting are accurate. So then I used a couple techniques, a magnitude and a frequency discriminator technique to get an even more accurate measurement. And I think I was able to get 4 significant digits of accuracy. And with these different techniques, and this is basically the tone that is telling you what the spin rate is. And this is at least a decimal point more accurate than the IC people were able to get from their data, and I don't know, I guess they didn't know what to make of this. It's like, who needs this much accuracy? But I thought it was cool. That you can measure something that's, IC was what, 20 light seconds or a minute, light minute away? And you could get data from a telescope and measure something like this accurately enough. I don't know, it just blows my mind. Okay, the next thing I'm going to show. Okay, we saw the Wi-Fi, this modulation, and I call it the IC IQ dance. It's a beautiful thing to see. And after I show it, if anyone in the audience has any ideas of what is causing the jitter and what is causing the compression, and you'll see what I mean. How does that look? So you can see that it's wiggling around. So we have the two symbols, and it's rotating, but then it kind of rotates to the left for a while, and then it rotates to the right, so it's jittering. And then if you look at the 2 points, they're going like this, which is meaning the amplitude is changing. But why is this happening? Arecibo, it's a super strong signal that we're getting from Arecibo. Space, there's nothing in, there's only 20 light seconds away. Why is the signal doing this? I don't know, you see this a lot in comms, but I would not have expected this from the signal. Oh, another thing I did was the wiggling drift that you saw that showed the spinning. I took that linear drift and I corrected it with a linear sweep. So the signal was, basically I mixed the drifting signal to baseband. And this goes on for a while. I don't know how much more you want to see of this. Anybody have any ideas of what's causing the somewhat random drift? I don't know the answer myself, so any guesses would be I'd like to hear. It would be very, very helpful. Okay. Okay, so I'm not going to show this because I don't have an internet connection up and running right now. But well, I have to test it to make sure. I'll try that last, because if it doesn't work, I won't be wasting much time. But basically, so everything that we saw was baudline. I created a program a couple years for a customer called it baudline EXA. It's the same baudline that did everything that you saw, but it has one special thing that it does. It's a very big data exploration tool, and it allows you to browse exabyte-sized data files. So you might have a terabyte drive on your computer. Imagine thousands of those. And that's not even an exabyte, but it's designed to random access and same real-time feedback latency that you have, but using a huge amount of data. And the demo I might show at the end, I SSH into the Amazon cloud, where I have a RAID set up, about 4 terabytes of data, and I'm going to run baudline remotely, and you just browse around, and it's just like you're using a local data file. Okay, for the next demo, baudline can play back data, as you just saw. You can browse pre-recorded data sets. And another thing it can do is it can record. So it can record, browse in a pause mode, and play. I'm going to use this SDR made by Newland. I'm going to be sampling at 40 megasamples a second. And I know we're at National Instruments in EDIS, and I would have brought my USRP B2010, but I don't have a case for it. And I don't like taking it anywhere because it's really expensive and I don't want to break it. So if you guys make a case, I'll bring my USRP B2010 to places like this. So I only use it at home now, but okay, so I have this set up to frequencies 2.4 gigahertz. And here we are looking at Wi-Fi flyby. I'm doing like almost 5,000 FFTs per second. I can, what can I do with this? We can pause baud line and scroll back at what we just looked at. See something interesting, we can zoom in on it. This looks like the Wi-Fi beacon. I can select some of this, bring up an average window, take that spectrum we just saw and paste it in. That's what it looks like. Kind of looks like the Wi-Fi beacon. Move this window over here. Scroll on some more. I could probably even take this. So this is a frequency across the side, and this is almost 40 megahertz of bandwidth. I don't think I've ever done this before, but let's listen. Let's slow that down a little bit. Okay, so that's what the Wi-Fi beacon sounds like. 40 megahertz wide of it. It's recording again. Get a different frequency. I'm looking at 780 megahertz right now. This is a lot interesting, more interesting before. Let's just give it a second. Can anybody guess what this is? Yes, it's LTE. And if somebody uses their phone on LTE right now, this will look a whole lot more interesting. This is, there it goes. It was going wild before I came up here. Okay, thank you. Thank you very much. So now we can scroll back and look at this. Yeah, LTE is a really interesting modulation. It uses OFDM, which is orthogonal frequency division multiplexing, which is what Wi-Fi uses, but it does it in small, what's the word they use? I have a word for it, like a super block or something. And you can use a small chunk of bandwidth depending on the capabilities of your phone. And some phones can use the whole, what is this, 10 megahertz wide about of the bandwidth. And it's really interesting to look at because it has holes in it. Because you only use the bandwidth you need. And 700, well, that's weird, 780 megahertz. This was a little strong, and I'm thinking it overloaded the circuitry, so it's a bit distorted. But anyway, back to recording. This is hardly using any CPU of the machine to do this right now. 40 megahertz of bandwidth. Speed this up a bit. Okay, so that's it for my real-time demo. And you can browse all over the spectrum, and I mean, as you saw in the previous talk, there's interesting stuff all over the spectrum. Okay, last section, mystery RF signals. I used to have a page that I kept updated on my website called the mystery signal page, and I kind of stopped a couple years ago after I did 20 or so mystery signals. But I'm going to start it back up again. I'm going to focus mostly on RF signals, and I'm going to do it on Twitter. So I'm going to post a picture and people can actually comment, because my previous, on my website, you just saw a picture and people emailed me and it didn't have the feedback. So hoping to revive it, and this will be a bit more user interaction. So I'm going to have signals like this. This is a warm-up signal. Anybody guess what this is? Yes, it's QPSK, quadrature phase shift key. 4 constellation points, and it can jump between any of the 4. It's packetized. This is actually recorded from SETI Quest, from the Allen Telescope Array, and they did something called an RFI test where they were just pointing at the horizon. So we don't even know what we were looking at or what the signal is. They just wanted to test how much interference from RFI there was. And just browsing through it, there's a lot of interesting stuff to look at. Okay. This is that signal that we saw before. And I'm going to play a demo of this. We saw this on SETI Quest. We don't know what this is. If anyone has any ideas after I play this, please let us know. It would be very helpful. Let me quit this. Okay, we can't hear anything, so let me slow it down a bit. So can you hear that fine out there? So let me jump back to the start. So it's this oscillating, this FM oscillated carrier just going back and forth. Has some distortion products really close to it that you can see. And then it just breaks into this wider band modulated signal for a while and then goes back to this oscillating carrier. We have no idea what this is, but it pops up occasionally in the SETI Quest data. So we're pretty sure it's terrestrial. It's strong, it's local. It's an interferer, we just don't know what it is.
Some kind of video.
I'm sorry, what do you say?
Video, when it starts modulating out, that's a more complex picture.
It could be. It's not too wide in frequency, though.
What's the modulation rate between each of the FM excursions? How long is it between?
Let me measure that. Okay, I'm just looking at my sample rate to see if this is really, that's really the sample rate. So the sample rate is 136 kilohertz. So we're looking at a path of it, so we're looking at around 60. This is around 60 kilohertz wide. So it's really not that wide band of a signal.
Vertically between the peaks?
Let me zoom in and I'll measure that. These are the periodicity bars, and I'm measuring that to be 10 milliseconds. But that's the accuracy of my measurement. Let me bring up a, this will tell us what the...
50 hertz CPU power supply turning on with spread spectrum, FCC.
98 hertz, so it's probably about 100 hertz.
Right, 50 hertz European spread spectrum CPU power supply turning on the demonstrator.
Could be, but the Allen Telescope Array is in Northern California.
Very sensitive.
You did say it was a very Yeah, that's right.
Yeah, they have 42 dishes, but I don't.
China, moon bounce in China.
Parts of Japan bounce electricity also.
China.
No, they actually use 300 and something hertz in aircraft AC power. It's a weird number.
And this was recorded at near the water hole, near the hydrogen line, 1422 megahertz. Okay, getting near the end. Okay, now so this is another mystery signal. IQ constellation plot. I and Q axis. Saw the QPSK before, kind of QPSK-like, but there's more points, and I don't know if you can see this on the screen, but you have transitions that go like that. There's grooves, and that's just caused by 8-bit quantization for our recording equipment, so just ignore the grooves, they don't mean anything. And the signal is carrier locked. So when I post this on Twitter, you know, can anybody guess what the signal is? And I'm not going to tell you what it is. It's a quiz. This one is two phases. It really does look like an equal sign. This is not squished because I changed the gain or recorded it incorrectly or anything. It's just a strange modulation that looks like that, and the carrier is also locked. And I have no idea what this signal is. This was recorded from the GOES 13 NASA satellite, and it was in a section that is not supposed to be used by GOES, and it's undocumented. So we can't figure out from the documentation what the signal is. It's a mystery. Maybe somebody's seen a constellation that looks like that before. We can go some clues. Okay, the Boilerline that you saw, Boilerline you can download on the web for free. It's an older version. I've been running a Boilerline beta for a while now, too long. I need to release it. Has a whole lot of new features. Everything you saw here used the beta. Everybody here, if you're interested and you'd like to download a version of the beta, let me know. I'll send you the link. Or you can just use the Boilerline that's on the website if you want. That's fine. And that's it for my talk. Maybe in the future, I had a DARPA project that I finished back in May called Weak Symbol Correlations. And great thing about the DARPA project was I own all the IP. I can talk about it, which is great. A lot of my customers, you know, I can't talk, whether they're the government customers or just a corporate customer, nobody likes you talking about what you're working on for them. But this was different. You know, I actually have a link on the DARPA website. They want me to talk about it. So I might do this as a talk in the future. So any questions? I will try the Boilerline EXA, but that won't be as interesting as the stuff that you just saw.
The IOC3 mystery jitter constellation, do you recall if that was an analysis of downlink signal when it was phase locked to the uplink, or whether it was just on the local oscillator on the satellite?
I think it was the local oscillator on the satellite because it was sending telemetry. Balint would know for sure because he knows the internals of the satellite a lot better than I do. Question was the IQ dance, where was the clock? Was it IC's internal clock, or were you sending up the clock and then it was?
No, the internal clock.
That was the internal clock. So a lot of problems with that clock.
Subjected to a few cosmic rays.
Yeah, well, it's 30 years of high radiation.
Well, with the offset BSK moving around, I wonder how Phil Karn's demodulator worked on that, because you have to track that.
Yeah, right.
And it's moving, but it's not moving that fast, so we probably could track the motion. But seems like a bit of extra work you have to go through to cleanly demodulate it. Do you know if it caused him any problems?
I think he managed to work around it. He did some analysis, if I recall correctly, and sort of built in some code to handle this. And even just doing it really simply in GNU Radio with the non-Viterbi version, that worked quite, you know, with the strong signal, that would seem to work quite nicely as well.
Mm-hmm.
Just tracking the carrier.
So some of it was caused by the spinning, but it wasn't constant.
Right.
You know, because it kind of went this way and then it went that way. It just kind of wandered around.
Yeah.
Any other questions?
Very interesting applications that could offload some of this massive computation onto FPGAs.
I thought about FPGAs. For the broadline beta, I've made a lot of SIMD, so vector processing, the SIMD instructions, SSE or AVX. The next version of broadline has a lot of, it's heavy into that. And you get quite a performance improvement. So not sure I really need more performance from broadline because the broadlines that you saw running were using just a couple % of the CPU. The graphics display takes the huge chunk of it. But for my DARPA project that I might talk about in a couple months, I used a Xenon Phi coprocessor, which had 2 teraflops. And the nice thing about the Phi is you can program it like you can a processor, as opposed to an FPGA. You have to do VHDL, or I hear they have C compilers from now, but you have to write the C a special way.
OpenCL stuff coming.
Oh, really?
Yeah.
All right, let's thank Erik then. All right, thank you very much, Erik. So I think we'll wrap up there for this evening. Thank you very much for coming to the inaugural Cyberspectrum meetup. I hope you had a good time. If you have any comments or suggestions or things you'd like to see or topics you'd like to present and so on, please feel free to email me, tweet, leave a comment on the meetup page, and also please, spread the word to people that you know, so get even more people excited about software-defined radio. So thank you very much again, and see you next time. And I also should say that thank you very much to Edis Research for sponsoring tonight, the beer and the pizza, etc. I think that that was quite nice. All right, thanks a lot.